both work and power have, pretty, meanings that are very much accepted in general language. But, this is physics, not general language, so we probably have different meanings than we're used to. So in order to do work in physics, we need to meet two main criteria and then one additional little criterion. So in order to do work in physics, we have to be exerting a force on the thing that we're doing work on, and that thing has to move. It also has to move in It needs to move at least a little bit in the same direction as the force. Alright? So if I want to do work to this folder, I need to exert a force on it, and it needs to move as a result of that force, at least partially in the same direction that I'm pushing on. So let's look at a few examples of work and no work. Let me pick something that I actually have to exert a pretty large force on. Alright, so here's my toolbox. Alright, it's not the heaviest thing in the world, but it's not that light either. Am I doing work right now? So we could be ultra nitpicky and say, yeah, you're not holding it still, it's shaking a little bit. But we're not going to be nitpicky like that. Right? So am I doing work? No. Am I exerting a force? Yes. I am exerting a force. If I wasn't, it would be accelerating down towards the floor, and it's not. So I am exerting a force, but it's not moving at all, let alone in the direction of the force. So no work if I'm just holding it here. What if I hold it out like this, right? Surely now it's much harder to do. So now I'm doing work, right? No, I'm not. Right? In fact, it's the same as before. I'm exerting a force, but it's not moving. Although this is much harder for my arm to do. So how about now? Yeah, I was doing work then because I'm pushing up and it's moving up. So I am doing work. How about now? But it's moving that way, not up.
But it's moving in the direction.
Alright, so I am exerting a force. And what is the direction of my force when I'm kind of moving it that way? I actually think it's still up. I actually think it's still only up. Because I'm not accelerating it, right? So I don't have to exert any force in the direction it's moving, since it's moving at a constant speed. So I would argue that I am still exerting a force up, and it's moving up and that way, but fine. Up and that way still has some up. So I am doing some work as I kind of move it diagonally. Questions about those examples or problems with those examples so far? Yeah, Victoria.
So you're doing less work if you're moving it diagonally?
If it has the same magnitude of displacement, then yes, I am doing less. But it depends on how far it's moving. Depends on how far it's moving. In the example I just showed you, yes, I think I was doing less work when I moved it diagonally. Other questions on those examples we looked at so far? Okay. How about now? Yes. So while it's moving down. So let's look at it in pieces. Am I exerting a force?
Yes.
Yes. What is the direction that I was exerting a force in? Up. Up. I have to still be exerting a force up because, well, number one, if I'm not exerting a force at all, right, then it looks like that. And it's accelerating 9.81 meters per second squared down. Right? That's with no force at all. If I'm exerting a downward force, then its acceleration would be even greater than 9.81 down. And it wasn't doing that. It was moving at pretty much a constant speed. I do have to push up in order to guide it down at that constant speed. So I am exerting a force. It is up, and it moved down. It is down partly the same direction as up. Not really. Not really. But I agree that that's a little weird. And it actually has a weird answer also that we'll come back to in a few minutes. So for right now, we'll say that I'm not doing work when I do this. Anybody want to guess what we're going to change that to in a few minutes? What?
We're going to change it to yes.
Well, we're going to change it to yes, but more specifically.
Wait, what was the question?
The question is, right now we're saying that I'm not doing work right now. We're going to change that in a few minutes to yes, I am doing work, and I'm looking for guesses about a more specific answer to that. Yeah? Displacement. So displacement is an important word here, but yeah, I think we need more than that. All right, so that's fine. We don't have to guess yet. Now, of course, work is a quantitative thing. And as a first shot at our equation, at our definition for it, well, anyway, capital W, right? That's our symbol for work. That makes sense. So at first glance, work is force multiplied by displacement. But that's actually only true if those are in the exact same direction. All right, so in the example when I was lifting up, then yes, the force that I'm using multiplied by the displacement would tell me how much more. In reality, we have to throw in a term to address what the heck happens if they're not in the same direction. So really, truly, work is force times displacement times the cosine of the angle in between those two vectors. All right? So if the force is up and the displacement is up, what angle is between those two things? Not a trick question. Yeah, 0. If the force is up and the displacement is up, there's 0 degrees between up and up. All right? What's the cosine of 0? How do we not know that?
1.
Cosine of 0 is 1. Right? And whatever, you don't have to know that. You have calculators that you can put that into. But that's actually a handy thing to know, that the cosine of 0 is 1 and the sine of 0 is 0. Right? Those are handy things to know. So anyway, if these two things are in the same direction, then I don't really have to worry about that since it gives me 1. Right? That's why I said that this top version is true if they're in the same direction. Now, what about the example where I'm pushing up, but the displacement is like horizontal? So like right now, trying to make it move horizontal. Am I doing work now? Well, I would say no. I would say I'm not doing any work. And I think we could explain that using our original definition up here, that I am exerting a force, it's up, right? The displacement is horizontal. There's no commonality between those two directions. It's not moving in the direction of the force at all. So I'm not doing any work according to what I said before. And then if the force is up and the displacement is horizontal, what angle is between those two directions? Force is up, right? Displacement is horizontal. All right, so yeah, I couldn't tell if you weren't answering because you hated me or you weren't answering because you actually didn't know. I think for at least some of you, it's because you didn't know. 90, all right, cosine of 90. Cosine of 90 is 0, right? So I'm not doing any work if those are perpendicular to each other. Questions about that before we readdress the kind of heading down one? Yeah, Bert.
So for force, are you calculating like the force that you exert on it? Because I know, like, are you calculating the net force? Because
no. So we're talking about the work that I am doing to the tool.
So you wouldn't.
So all we care about, and I'll let you ask a follow-up, and let me finish answering that one. All I care about is the force that I'm exerting on the toolbox. Go ahead.
All right. Yeah, I got it.
Good. No follow-up. All right. So let's do this one again, right? Look, stop taking notes for a second. This one again, where I'm moving down. Okay, the direction of my force is up. The direction of the displacement is down. What angle is there between those two directions? 180. Right? 180. What's the cosine of 180 degrees? Not 0. -1. -1. So in the instance where our force and our displacement are in opposite directions, we're actually doing negative work. Or you could say that it's doing work to me, but I'm doing negative work to it. Right? Maybe that's a little weird, but that's 100% technically correct, and now we actually know everything there is to know about work. Follow-up questions. At this point, we'll do some examples for homework. We'll do one example in a few minutes. The follow-up issues about doing work, not doing work right now. All right. So is the Earth doing work to any of you right now? I'm getting 2 of these. I'm getting a bunch of these.
Yes.
Is the Earth exerting a force on any of you right now?
No.
Is it based on a reference
The Earth
point?
is exerting a force on you. Yeah, gravitationally, right? We can even quantify that. It is exerting a force on you. Is it causing you to move? That force is not causing you to move. None of you are accelerating towards the Earth right now. But if your chair gave way, then the Earth would be doing work to you, right? Because it's pulling on you and you move in that same direction. So the Earth can do work to you. It's not doing work to any of you right now. All right, what we didn't address yet, I forgot, is what the heck unit work is measured in, because it's a new unit. We haven't seen this one before. So let's see, the unit of force is the Newton. The unit of displacement is the meter. What is the unit of this angle? Degrees, and what is the unit of the cosine of an angle? It doesn't have it, right? The cosine of some it's unitless. So Newton meters is our unit that work gets measured in. That is important enough that it gets its own name. That's called the joule, Joule, right? Capital J. And you should have seen that in chemistry last year, yes? Yeah, maybe like thermal energy, right? Yeah. So energy, which we'll talk about either Tuesday or Thursday, also is measured in joules. It's intrinsically related to work. All right, any other questions right now about work before we spend 90 seconds talking about power? Great. Power is way easier than work, right? Power is simply the rate at which work is done. Right? Work, how much work we do divided by how much time it takes us to do it. That's it. Right? There's nothing more to the story. Well, we need to know what it's measured. There's nothing more to the story. There's no additional complexity. We said work was measured in joules, and time is measured in seconds. So power ought to be measured in joules per second, but that's important enough to have a nickname also. What is it? We did the reading. Holly did the reading. Watts. Right? So power is measured in watts. The symbol for watts is a capital W. I hope that's not confusing, that it has the same symbol as the variable work. That doesn't usually yield much confusion.
Wait, just capital W always have to be the symbol for work, or using lowercase w?
Does capital W always have to be the symbol for work? Yes, it does. Lowercase w does not represent anything that I'm aware of. The omega, which kind of looks like a curvy lowercase w, that's our angular velocity symbol. But no, work has to be capital W again. So let's do one example of finding a work and a power. We'll see if there are any follow-up questions. Then we'll do our review of chapters 1, 2, and 3. And then if we have time, which I hope we will, I think we will, you guys will calculate how powerful you can be while doing some moderate exercise. So, all right, Barbara pushes on a couch. Right? There's probably going to be some friction. So she actually has to push pretty hard. And she moves the couch 2 meters. Right? Not very far. It takes her a considerable amount of time to do that, 4.2 seconds. I'd like to calculate how much work she does. I would also like to calculate how powerful she is. So I'm going to draw a picture, right? That's the first thing that we do. And I'm going to kind of draw the couch. I don't know how to draw a couch. There's armrests. All right, there's the floor. Here's Barbara. She's pushing on it. And that's probably good enough. I don't really want to do a free body diagram. I don't really want to do a motion diagram. This is a trick question, right? Is she doing work or no? Is she doing any work? Yeah, she is doing. No, she is doing work because she's pushing. Well, presumably, unless she's a total idiot, she's moving it. Well, she pushes horizontally. Right? Presumably, she wants to move it horizontally as well. So yes, I do think she's doing work. She's pushing horizontally. It should move in that same direction. So what the heck do we know? The 185 newtons, that is the force that Barbara is pushing on the couch with. I'm just going to call that F. If the couch only moves in a single direction, then the displacement would be 2 meters. 4.2 seconds is the interval of time that it takes her to do that. And we're looking for how much work, and we're looking for how powerful she is. Questions from anybody in my step 1, my step 2, or my steps 3, or on that, we already established she is doing work. If there's any follow-up questions on that, ask that. No, all right. So I'm going to find the work first. Our equation for work was force times displacement, and since these are in the same direction, I'm okay with you leaving out the cosine theta term. I'm going to leave it. I'm okay with you leaving it off if you establish they're in the same direction, but I'm going to go ahead and leave it. So I know the force is 185, the displacement is 2.0, and then what's the angle between the two things? 0, yeah, 0, right. So you push it in the same way as it moves, so that would be the cosine of 0 degrees. All right, so the cosine of 0 degrees is 1. Maybe I should deal with that first. Oh boy, significant digits for that. They're in exactly the same direction, so I would not let that 0 limit my significant digits. So this would be like exactly 1. So 185 times 2, somebody back me up on this, but what was that, 370? And that should have 2 significant digits, it does, and my unit is joules. 370, capital J for joules. Pause for 10 seconds and see if we have questions about that first part. Follow-up questions from anybody about Garber doing positive 370 joules of work? Okay, power. Right? Power is the rate at which work is done. So my work was 370, and that was not rounded really, so I don't, I can keep extra digits, but it looks the same way. And then the time interval is 4.2. Is that 88? 88. 88 watts. Right? 88 watts. That's about the same power as like a light bulb. Follow-up questions for anybody on this first example of work or power? Yeah, there's not a whole lot of complexity, especially if our force and displacement are in the same direction. But if we can establish that, there's very little complexity. All right, so that is really all that I have to say about work and power. We will have some homework to go over, right? We'll see some more examples. That's all I have to say. Before I review chapters 1, 2, and 3 with you, I do want to clarify what I said was the only midterm review assignment. I gave you guys that big packet. Did I give that to you electronically and hard copy? I did give you both. Great. Now, one of the, and I can pull it up right now in case some of you might not have looked at it since I gave it to you 2 weeks ago. Maybe it was more than 2 weeks ago.
A couple questions, they're missing a graph or something. So
Say it again, Bert.
A couple of questions, they're missing a graph.
A couple of the multiple choice questions, or on this, or?
I think they're multiple choice.
Yeah, if they're missing on the multiple choice, there's nothing I can do about that. I think I gave you that electronically also. So if you open it in some other, you might have a better version of Microsoft Word than me. You might be able to open it in something better. I don't have the ability to give you anything different for that. So sorry about that. All right, so that stuff, you're on your, that you don't have to do. That's up to you. But what I am asking you to do is each of you will be answering 2 of these essential questions that are embedded in the topical outline. All right? In fact, a couple of you might only have 1 to do if you're at the end of the alphabet. So what I'd like to take a minute or 2 to do is tell each of you which questions you have to answer. So if you have this with you, it probably makes a lot of sense to just write it right on there. If you don't have it with you, you have to write it in a safe place. And there were actually only 3 units of study here. So you'll be assigned a question from Unit 1, Unit 2, and or Unit 3. And then I'll tell you which unit and then which question number. So this first section we're looking at is actually section 1, and there's 8 questions there, right? So the first 8 of you, I'll say section 1, question whatever. All right, questions about what the heck I'm talking about before I tell you which questions you have to do. All right, so I guess the simplest way for me to do this is go alphabetically and give you both your questions at the same time. So Alec, Unit 1, Question 1, and Unit 2, Question 13. Lauren, if you choose to watch this, Unit 1, Question 2, and Unit 2, Question 14. Henry, Unit 1, Question 3, and Unit 2, Question 15. Tim, Unit 1, Question 4, and Unit 2, Question 16. Julia, Unit 1, Question 5, and Unit 2, Question 17. Nithya, Unit 1, Question 6, and Unit 2, Question 18. Sakif, Unit 1, Question 7, and Unit 2, Question 19. Emily, Unit 1, Question 8, and Unit 2, Question 20. Jesse, Unit 2, Question 1, and Unit 2, Question 21. Alex, Unit 2, Question 2, and Unit 2, Question 22. Victoria, Unit 2, Question 3, and Unit 3, Question 1. Emma, Unit 2, Question 4, and Unit 3, Question 2. Teresa, Unit 2, Question 5, and Unit 3, Question 3. Hannah, Unit 2, Question 6, and Unit 3, Question 4. Holly, Unit 2, Question 7, and Unit 3, Question 5. Sophie, Unit 2, Question 8, and Unit 3, Question 6. Kara, Unit 2, Question 9, and Unit 3, Question 7. Shruti, Unit 2, Question 10, and Unit 3, Question 8. Jane, Unit 2, Question 11, and Unit 3, Question 9. And Burton is the only lucky one, Unit 2, Question 12. All right, if you missed it or want to check, you're going to have to do that with my hard copy later on. All right, so what do you have to answer your 2 questions, and I expect you to answer it correctly. I haven't 100% decided how I'm going to have you answer them, so let me share my thoughts, and if you have opinions, you can chime in. What I'd like to do is like a Google document that you can put your answer as a comment at that question. However, a few of the questions involve drawing or graphing, and I don't think that's a conducive method for those questions. So what I'm thinking about, and I'll commit to this when I see you on Tuesday, is a Google Doc where you'll answer in a comment if you don't have a drawn one, and then if you do have a drawn one, you can hand in a hard copy, and I'll like put them in the window or something, post them in the window or something. Anybody have thoughts specifically about those drawing, graphing ones? No? All right. So unless I have a better idea, that's what I'll be telling you on Tuesday that you'll have to do. And I think I want these done by like, so I need to chime in on the correctness of your answers, right? If you're using this as a study tool, you need to know whether these questions are right, whether the answers are right. So what I think I'll be doing is making this due like Thursday early evening, right? And then that would allow me to go through them all at least before the weekend starts. So expect me to formalize that on Tuesday, that you have to submit it in a Google Doc unless you have a drawn one by Thursday, maybe like 5 p.m. And then, by Saturday morning, I will have confirmed that everything's right. Yeah, Holly. If it doesn't ask for an explanation, you don't need to explain it. You're welcome to. But if it really just is yes or no, then you could just say yes or no. Yeah. All right, any other clarifying questions about those essential questions? Yeah, Jane. The only thing that it's possible that the last question, yeah, you might have question 3, number 9 that we haven't covered yet. In fact, we might not cover that until Thursday. Fortunately, most of these questions will take like 90 seconds to answer. So if you know that you're going to have difficulty like between, Thursday at 2:15 and 5 o'clock, finding 90 seconds online, talk to me. But you're probably the only person that applies to. So if you know you're going to have difficulty, talk to me. I can just give you that lesson like, early if you need it. All right, any other issues about those essential questions? All right, great. So that brings us into our first chunk of midterm review. And I'm really just biting off chapters 1, 2, and 3 today. After our big quiz on Tuesday, I'll probably bite off chapters 4, 5, and 6. And then I don't think I'm going to review chapter 9 or 10 or 11, right? Because we kind of just did those. So we'd be looking at Tuesday, 4, 5, and 6, and then Thursday, 7, and 8. So what I'd like to do is just kind of remind you what was in each of those chapters that you're responsible for, the big things that are in those chapters, and then I do actually have some practice questions for a couple of those pieces. So anyway, chapter 1 we kind of skipped entirely back in the first days in September, but we've actually talked about quite a few of the things in chapter 1. So some of the things that we've talked about that now I do expect you to know. I never have a pencil sharpener in here. Significant digits, right? Obviously, you need to know. It's not going to be make or break for your test grade, but yes, there are going to be questions that involve significant digits. Measurement and precision is actually something in Chapter 1. So all these things that I've been nitpicky with raw data and with labs, Chapter 1 actually talks about those things. And then also graphing rules are talked about in Chapter 1. We are very strong with the graphing rules, but sometimes we have lapses. So for instance, with the lab reports that you just got back, I did have, I think, 2 people out of 40 that made a graph of period squared versus radius, but they didn't have a consistent scale on one of their axes. Right? So there was the 2 people, I don't know how the heck you did it, I don't know what graph you told Excel to make, but it just used your radius values like in order of how you had it in your table. So it went like 0.2, 0.5, 0.3, 0.9, like you know you can't do that, but I think whoever did that just didn't look back at what Excel printed out. Right, so that's the kind of graphing rule that Chapter 1 talks about. So Chapter 1, I don't really think you need to go back and study for midterm purposes, but we have talked about quite a few of the things in there. Chapter 2, we did spend a tiny bit of time drawing motion diagrams. And in fact, we did them for many of our early problem-solving strategies. And motion diagrams were when we kind of drew the dots to represent the position of our moving object at equal time intervals. And if we had evenly spaced dots, we said that that had to mean that the thing was moving at a constant velocity, right? Because of equal time intervals, it's covering the same displacement. If we were accelerating, then we typically saw the dots getting further and further apart, unless it was a negative acceleration, and then we probably saw the dots getting closer and closer together. All right, so this was not a huge thing. We didn't really stress this at all, but we did talk about motion diagrams, and that might be something that you've forgotten in the 3 months since. Coordinate systems, I think we used that word, but coordinate systems really were a way of being able to quantify our position of objects, right? So when we did projectile problems, for instance, you were forced to use my coordinate system. So if we have the kind of projectile problem where we fire something off of a cliff, maybe horizontally, right? I forced you to use a coordinate system that had a horizontal position of 0 where we launched it, and then the direction of motion would be the positive direction. I also forced you to have, like, the ground level be a vertical position of 0, and I forced you to have up be the positive direction. So those are just examples of coordinate systems, right? We need to establish where's a position of 0, and then which way is positive, which way is negative. Chapter 2 also introduced us to vector and scalar quantities. Vector quantities were ones that have to have direction reported with them, and scalar quantities are ones that do not have to have direction associated with them. So thinking about some of our more recent variables, right? Momentum is supposed to have direction, so that is a vector quantity. Impulse is supposed to have direction also, that's a vector quantity. Time interval is a scalar quantity because 2 seconds, up, I don't really know how that's any different from 2 seconds east, right? Direction is not important for time intervals. Time interval, right, real simple, just the amount of time between 2 events. Symbolically, we call that delta t for the change in time between that initial and that final event. Displacement was our distance between where we start and where we finish with direction. So displacement was a vector quantity. We denote that with a delta d for change in position. And then we went pretty slowly and spent a lot of time with our position versus time graphs.